as we mentioned, one of the getting a new space to hang around in is really exciting. But even more exciting is the fact that we've hired amazing new people to come figure out how we're going to make the most of this space and push things forward. So we thought it would be fitting for this event to ask some of the more recent arrivals to come and give us a quick overview of their research and what they're excited about. So that's what we're going to do, and we're going to start off with Becca Willett.
Hi, thank you very much. It's my great pleasure to be here at the University of Chicago and to be here today for the opening of the new building. So I work in the field of machine learning, where we're trying to train computers to understand something about the world from examples. And that means many different things to many different people. But today I'd like to tell you about one specific example of ways that we are using machine learning, I think, in a creative and novel way. And so I'm going to tell you about some current work that I'm doing with my student, Davis Jilton, and postdoc Greg Anji, who are here in the audience today, on learning to solve inverse problems in imaging using machine learning. So inverse problems in imaging show up in a wide variety of contexts. And the basic idea is this. We've got some image, we're going to call it beta, and it's just a list of all the pixel values that we're ultimately interested in. But we don't get to observe it directly. Instead, we make some kind of distorted measurements of it. So for instance, we could be missing a big block of pixels in the middle of it, or each one of those pixels could be corrupted by errors or noise, or we might observe a low resolution, small version of the image that we ultimately care about. And so what we'd like to do is to take these noisy or distorted measurements and figure out what the original underlying image is. So in this model, we're going to have Y, which is our measurements, and a big matrix X that corresponds to the distortion that's sort of messing up our image. And so the question is, well, what's the right way to figure out what beta is, our image, from our data? So classically, the way we would approach this is something like this little toy block diagram, where we would take our distorted image Y, and then what we would do is we would search over all possible candidate images beta. And we would check for two things for each one of these candidate images. First, we would say, well, does it somehow match our data? Is it a good fit to the data? And second, does it fit our kind of model of what we think good images should look like? So does it look does it look nice and non-distorted? And so we would do this search over all candidate images, pick one that satisfies both criteria, and that would be our estimate. So the name of the game is really choosing this regularization function, R, that somehow codifies what we think should be in images, what the natural geometric structure of images should look like. So there's multiple levels of enlightenment for image reconstruction. Classically, what we would do is we would predefine this regularization function R, say that images that we care about are smooth, for instance. Bayesian statisticians would take a stab at this and say, well, let's define a probability distribution over all possible images so that nice, good-looking images have a high probability and images that look like snow on the old style television screens have low probability. But the next stage of enlightenment is to really say if we've got huge training sets of images, can we somehow use that to learn a regularization function that we can maybe plug into this framework? And so researchers have been studying exactly that. And as we talk about it, we're going to focus on trying to do this without necessarily needing millions and millions of images. And this is especially important in things like medical imaging, where we might not have millions and millions of images to play around with. Okay, so here's one approach that people have considered. They said, let's pretend for the moment that we have this regularization function R and think about how we would go about doing this search over all the images. And a lot of algorithms operate something like this. You would start with some initial guess, and then you would go back and forth between two steps. First, you would try to perturb your image to be a somewhat better fit to your data. And second, after you've done that perturbation, you might have introduced some distortions, and so you try to smooth out or correct those distortions by applying your regularizer. So since we know that that's what we would do if we already had a good regularizer in hand, researchers said, well, okay, let's now just replace this smoothing out the errors process with something like a neural network. So let's go and take our training data and try to learn a good neural network that maps a somewhat noisy or distorted image to a nice, clean, beautiful image. And once we've trained that network, we can just, bam, plug it into this optimization or search routine. And so that sounds all very well and good and exciting, except it really doesn't work that well. Or it works very well as long as you've got 100,000 images or more. But if you have fewer images than that, if you're in something like this medical imaging context, then things just work terribly. You get complete garbage out of it. In fact, this is such a big problem that people like our president have commented on the failure of convolutional neural networks and have said what a travesty this is. Okay, so what we'd like to do is to do something better, because really it's not the CNN themselves that are at fault. So let's go back to this optimization, or let's think about why this problem was doing so badly. So I said we needed a neural network that could take in an image that is potentially noisy or a little distorted and output a nice, clean, good-looking image. But in that process, that's a really hard thing to do in general. And one of the reasons why it's sort of an overkill is that for something like in-painting, where we're trying to fill in a bunch of missing pixels, what we're doing with this neural network is solving a much harder problem. So we're trying to reconstruct all these pixels on the periphery that are totally irrelevant to the missing pixels we're trying to fill in. So we're solving a harder problem than we need to, which means we need a lot more data. And instead, you might think, well, wouldn't it make more sense if somehow I was feeding in this image with the missing pixels, and all I needed to get out were those missing pixels? Then that requires a lot less data, you would think. And in fact, that's exactly right. So here's another look at this. So we started here before with this sort of optimization procedure, and we said, well, let's replace this second step with a neural network. But now what we're going to do is we're going to think about this as one giant block diagram. Okay, so each one of these dashed line blocks corresponds to these two steps, where first we are going to perturb things more towards our observations, then we apply our regularizer. Perturb towards our observations, apply the regularizer. So it's very much the same thing as we saw before, but now, instead of trying to train the network totally independently of our inverse problem at hand, so instead of ignoring the fact that, say, we ultimately want to fill in missing pixels, we're going to train this huge block diagram end to end and take into account from the beginning, throughout the training process, that there's a particular inverse problem that we care about and that we want to solve. And it turns out that this makes a huge difference and gives us huge improvements we're going to see in a minute. But one way to think about it is that this whole big block diagram corresponds to one giant neural network. And what we're doing is we are using our knowledge of the problem we care about, the fact that we're trying to solve this inverse problem, to somehow constrain what some components of this neural network look like. So they're not just arbitrary, but they're somehow constrained by the problem at hand. So I want to talk about how we can go about doing even better than this. So we started with this sort of approach that was based on optimization theory, except that the underlying theory of optimization doesn't really apply here because we're talking about neural networks that are non-convex. And so you really can't just blindly chip away at machine learning problems and expect to make huge advances. And so what my group and I have been doing is trying an alternative approach where we've been digging into ideas behind Banach fixed point theory and operator theory to provide additional insights into what the architectures of these neural networks should look like and how they can be leveraged into getting better reconstructions with less data. So what I'm going to do is just wrap up with a couple of examples here where we can see on the first column the original images, the second column what's being input. So we have an example from in-painting where we're filling in missing pixels, a compressed sensing example, a super resolution example, and a denoising example. And that middle column is showing that if we ignore what inverse problem we're talking about, then we really do badly. The fourth column shows that if we adopt this optimization perspective, flawed as it is, then we do better, but still we can do better still by adopting these new theories from operator theory and using them to guide the architecture of our neural networks. And so we were reaching or approaching the final level of enlightenment, perhaps, where we're really using some beautiful mathematical theory to guide network architecture design. Thank you very much. I'd be happy to answer any questions. Oh, it really was like lightning. Yes?
So, can you go back to the architecture? Are you
Sure.
repeatedly applying the network to the input image, and then like those are residual connections with like the previous version of the input image?
Yes. So in our new architecture that I didn't fully describe the derivation of here, there are some kind of skip connections, and there are reasons to think that that's advantageous for a number of reasons. But it wasn't something that we just sort of blindly put in there, but rather they fall out naturally from thinking about different elements of operator theory. So they're very mathematically motivated, and it helps us try to understand when and where they're going to work, and maybe more importantly, when and where they're going to break down. And when you think about people trying to understand images and things like self-driving cars, you really want to have some good mathematics and theory behind that. Yes?
Give us some more introduction behind this Banach fixed point theory. What is it about, and why it's useful for neural networks?
Oh, I would love to talk about that with you, but I think I'm getting the high five. So could we talk about it during the break?
Yes.
Okay, great. Thank you very much.
Hello, everyone. And I'm Aaron. I'm a new complexity theorist here, and today I'll talk about the sum of squares hierarchy, which I've been focusing on for the past few years. So here's a little taste of the sum of squares hierarchy. Let's say we have some polynomial p, and we want to show that p is not negative for all real inputs. So for example, let's say p of x was x squared minus 2x plus 2. So how can we prove this? So one thing we can do is we can use calculus to find the minimum value. But another way is to just write p as a sum of squares. So here, p of x, we can rewrite it as x minus 1 squared plus 1 squared. And since squares are non-negative, if we're looking at the real numbers, p is non-negative. So this idea that squares are non-negative is simple but surprisingly powerful. So now, what does the sum of squares hierarchy do? Well, the only tools SOS uses are this fact and basic algebra. That said, SOS automatically finds any proof which only uses these tools. And what this means is that SOS is powerful enough to actually capture a lot of the reasoning that we can do. Yet it's simple enough that we can bound its power. So just to highlight that SOS is indeed formidable. So at first, there were several algorithms which were discovered directly. Gomez-Williamson for max cut, the Gomez lineal relaxation for sparsest cut, analyzed by Aurora, Rao, and Bazarani, and the Aurora-Barak-Stoyer algorithm for unique games, which was realized that SOS captures these algorithms. In the past few years, there have been many problems where SOS has been applied directly. And I should note that SOS is often too slow to run in practice because it involves huge semi-definite programs. But it has been useful in control theory, where it's important to make sure that polynomials are non-negative, but there's only a few variables. Okay, so the fundamental research question, which I look at in various settings, is what is the power and limitations of the sum of squares hierarchy? So I think a good illustrative example is the following Turon-type problem, which Professor Rasberg told me about. which is what is the minimum number of triangles in a graph G with a given edge density. So it turns out that if you can take k-independent sets of size n over k and have all the edges between them, this is optimal. And this gives a bound which is essentially due to Goodman, which is the following, but it's not important what that exact expression is. Rather, and here's a picture of this optimal case. So we have our 3 independent sets and all the edges in between them. But what if we can't partition G evenly into these independent sets? So in that case, so it turns out, and this was only proved by Professor Rasbrove in 2008, that it's asymptotically optimal to partition G into independent sets where all of them except one have the same size, and the last one is smaller. So here's a picture of the solution there. So now what does SOS say about the triangle problem? So SOS easily captures Goodman's bound. However, one weakness of SOS is that SOS has difficulty capturing arguments that things have to be integers. So it turns out that low-degree sum of squares thinks that there can be k-independent sets of size n over k, even if k is not an integer. So low-degree sum of squares just gives Goodman's bound and doesn't capture Rasbrove's very technical proof of the true answer. So this is the power and limitations of sum of squares in this setting. So now I'll talk a little bit about some of my work. So I highlighted my previous work. I was looking at sum of squares on planted problems. So in a planted problem, you're trying to distinguish between a random input and a random input with a planted solution. So a classic example of this is the planted clique problem, where you're trying to distinguish between a random graph and a random graph where a clique of size k has been planted. So here's an example there. So in one of these two graphs, I planted a 5 clique. Any guesses on which one? It is indeed the one on the right. And why did you guess that? Actually, that's an optical illusion. The graph on the left has more edges. They're just like on the outside and look small. But yeah, the graph on the right does have the planted clique here. So over a series of papers, my collaborators and I proved almost tight lower bounds, sum of squares lower bounds for planted clique, and developed techniques for analyzing the performance of sum of squares on other planted problems. And now I'll say a few things which I'm currently thinking about. So one topic is sum of squares on robust estimation problems, where so in robust estimation problems, you're trying to make estimates even if like a small portion of your data is arbitrarily corrupted. So another topic is unique games, constraint satisfaction problems, and sum of squares. So a major open problem is what is the performance of sum of squares on unique games? And a question I know there's currently thinking about is can we verify the predictions of the unique games conjecture for how SOS performs on CSPs? And a third thing I'm thinking about is sum of squares and proof complexity. In particular, can techniques used for analyzing sum of squares give insight into other proof systems, such as resolution? And in particular, can we prove resolution size lower bounds for the planted clique problem? Okay, so that's all. Thank you.
Any questions for Aaron?
So question from a non-theoretical computer scientist. Could you go to your previous slide?
Yeah.
So what do you mean by unique games? I'm confused as to what you mean by a game in this slide.
Okay, so. Yikes! Do we have markers? Ah, thank you.
If you didn't have markers, it's dumb stuff. You should add that to the list.
We have them and they disappear.
See.
Okay, let's see. This is the question.
Yeah, so I guess it's. So in the unique games problem, we have the following kinds of constraints. Right? So at every node we have several different choices for what it could be. And the constraint is that, like, if you know the value here, then it maps to a unique value there. That's why it's called unique games.
Oh.
So so I guess it could look like this, for example. So if you're looking for a perfect solution, then it's easy to check whether there's a perfect solution or not. The unique games conjecture is about what happens if you're only looking for a solution where 1 minus epsilon of the constraints are satisfied. So now there could be like a small fraction of errors, and this as far as we know could throw everything off.
Okay. Thank you.
Thank you, Aaron.
Okay, thanks for coming. My name is Junchen Jiang. I'm assistant professor here. Just a big background of myself. I was born and educated in China. I received my PhD degree from Carnegie Mellon last year. My PhD thesis was about improving quality of experience for internet applications. I joined UChicago as assistant professor this summer. So what is my research? My research focuses on network systems such as the internet or cloud systems. And in particular, my research is driven by 2 recent technological trends. Okay? First, computer systems, network systems are becoming increasingly complex. Okay? And second, people now have better tools to collect massive measurement data, process them, and extract insight all in real time. So my research seeks to embrace these 2 trends by exploring the opportunities of harnessing the power of data and machine learning to improve in systems and networking research. And I call this new paradigm data-driven networking. Now let me explain these 2 trends in a bit more details. Now when you think about internet, right, so you think about applications like watching Netflix videos, browsing news websites, or making Skype calls or Google search and so forth, right? Now one thing shared by these applications is that they're all eyeball economy, meaning that it is very crucial for these applications to maintain a very high level of user satisfaction, which could mean very short web page loading time or very smooth video streaming experience, right? Now, at the same time, also you need to realize that users are becoming less and less patient. So to meet this increasing amount of user expectation, these applications have evolved over the decade into very complex delivery systems that are very complex and unwieldy. Okay? And now what's worse, because the internet architecture is federated, which means each delivery system has to go through multiple service providers. Each going to apply very complex proprietary optimization techniques on their own systems independently to each other. Okay? Now, on the other hand, however, the eyeball-driven nature of these applications actually means that these suggest that all the service providers, such as Microsoft, Netflix, or even Comcast, or AT&T, they all care about one single metric, which is user satisfaction. Okay? So as a result of that, application providers like Microsoft and Netflix have deployed massive client-side instrumentation scripts to measure the quality perceived by every single user and collect this measurement data all in real time. And at the same time, internet service providers like AT&T, Comcast are also deploying software-defined networking techniques that enables real-time telemetry from their own infrastructure of switches and routers. So as a result, there's a dramatically increased amount of measurement data from users and devices. So if we combine this growingly complex network system on one hand, and more and more measurement data directly about user perceived quality on the other hand, right, this is the opportunity of data-driven networking. Now, essentially, we could harness the power of data and machine learning to optimize networking system performance to better meet the needs of users and applications. Now, let's look into one particular example of data-driven networking in action. So here the application is video streaming, okay? The goal here is to provide a high video resolution with smooth streaming experience. That means there's no buffering when you start watching the video. Now today, when you watch a video on Netflix, essentially you're establishing a session, a video session with their service. Okay? And each session has multiple configurations, such as the server from which you stream the video, or which resolution you should stream the video in. And these configurations can hugely influence the quality of a user that the user sees. And these configurations also need to adapt over time with changing network conditions. But traditionally, these configurations are set by each video session individually, and will only change when video starts to buffer. Now, in contrast, what data-driven networking can do is that we can leverage the quality measurement data that these, say, Netflix is already collecting from many users and build a real-time machine learning model and use it to proactively configure, to adapt the configuration before video starts to buffer, right? Now, here are two graphs that shows the improvement by applying this data-driven idea on one of the most popular music video websites in the US. Left-hand side is buffering time, lower the better, obviously. Right-hand side is video resolution, higher the better. Now you can see that this data-driven networking idea can reduce the buffering time, at the same time also let user watch video in higher resolution. Okay. Now finally, the internet today is not only used by user-facing applications like video streaming or web, but increasingly the internet is sending data that are not used by human beings, but used analyzed by machine learning models. Okay. Now, one example here is smart cities. For example, smart city will collect a lot of video feeds from surveillance cameras or traffic cameras to a cloud server, and the cloud server will analyze these videos, feeds by some computer vision technique, computer vision models, rather than human inspection. Now, here is a graph that shows the amount of video data that are generated by newly deployed video cameras every day, and which you can clearly see that there's a super linear growth over the time in the camera videos that need to be analyzed. Okay. Now, today, if you think about these video data are actually handled by the same kind of network stack that are just like the ones you use to stream video for people to watch. Okay? But this is hugely inefficient because a machine learning model may have an utterly different set of requirements than a human viewer, right? For example, the machine learning model doesn't really care whether the video resolution is high or not, whether it doesn't care whether the video playback is very smooth or not, right? All it cares about is whether the video includes enough pixels for it to extract patterns, to identify patterns, right? So here, the architecture of data-driven networking would be a natural fit because you can simply rely on the feedback of quote-unquote users, which in this case is machine learning models, to directly drive the kind of decisions like how the video should be encoded, should be streamed. Okay? And in other words, the network stack can be tailored to meet the need of machine learning models. Now here's one of our early results. We basically stream videos from a camera via a narrow bandwidth-constrained narrow connection to a server which runs a object detection, deep learning-based object detection model. And we compare our data-driven networking approach with basically stream the video in the lowest resolution possible while still allow the server to detect objects correctly. And I compare that against the sort of traditional video encoding method, MPEG, that encode the whole video with varying quality levels. Yeah. And so basically you can see here that this data-driven networking idea can dramatically reduce the bandwidth consumption, but still achieve much higher accuracy. So to sum up, my research seeks to use data-driven and machine learning techniques to improve network systems performance, which is driven by the two of the recent trends of growingly complex internet systems and more direct measurement from users and devices. And this new paradigm of data-driven networking is powerful. It can be applied to both user-facing applications like web and video streaming, but also machine learning applications like smart cities. And the technical contribution will lie in the integration of advanced machine learning frameworks and data and domain-specific knowledge to improve network performance and resilience with data-driven insights. Okay, thank you.
Questions for Junchen?
Oh, yes.
So I'm really intrigued by this idea that machines appreciate video differently than humans do. I'm kind of wondering, do you have any ideas, like kind of what the limits are on that in terms of, what's the potential? It seems like there could be really huge differences in efficiency if you, and I'm just wondering what kinds of, are we talking about a factor 2? Are we talking about order of magnitude? Are we talking about a couple orders of magnitude? I mean, any thoughts on that?
Right. A good question. So basically, what's the, how large the difference would be if you let a user watch a video versus if a machine let machine watch the same video? Can you send probably like maybe stream 1 megabyte per second of data versus 1 kilobyte per second of data, right? So that's kind of a 3 order of magnitude difference. And here's, this is almost 3 magnitude of difference in terms of bandwidth consumption. The gain comes from multiple places. So one thing is, when a user watch a video, it needs to watch the place, persons or cars or objects, but also the background, right? But the machine learning model doesn't care about background that much. So that's one gain. The other thing is when videos are, when you let people view a video, you have to let the video play smoothly, right? But machine doesn't care about that. All I care about is whether you see an object here, saw an object there. Maybe I can do interpolation between these two places. So there are a lot of things. Now, to be honest, I don't have a good answer like how much potential gain it might be. Machine learning model is a moving target too, right? But I totally believe this could be even more than that. This is just a early study. I'm just studying this, but I'm totally happy to answer that question maybe in 3 years.
Okay, thank you.
Thank you.
Is that me? Yes. Cool.
So, hi everybody. My name is Sanjay Krishnan. I'm a new assistant professor here at the University of Chicago Computer Science Department. And so today there's been a lot of discussion about machine learning and AI. One of the questions that has always interested me is how can some of those wins that we've seen in machine learning and AI actually be used to make data analysis easier? Okay? So to sort of understand how we can start chipping away at this problem, let's start off with a really classical problem that has been studied in database research for the last 40 years. So there's this problem called query optimization. So suppose I have a database of 3 different tables: employees, salaries, and tax codes. And I want to answer a query, or I have a question on this data that integrates information from all 3 of these tables. Okay? So like calculate the total tax owed by all the employees. Now the problem is that's really easy to say in English. The second that you go down to try to write code to answer this question, there are many different options, right? You could scan the employees table first and then build up a lookup table on the taxes and salaries and merge those in, or build a lookup table on taxes and salaries, the Cartesian product of that, and then scan the employees, or should I first sort the employees by their position and then combine the thing? There are all these different choices that you have. So under the hood of every database system today is something called a query optimizer that takes a statement in SQL or some other higher level language and converts it into something that is an actionable program. One of these things, right? Because that SQL doesn't actually tell you which order or what to do first or what to do second or where to build indexes or where to sort something, right? So the way that this works is that anytime you have these kind of planning and search problems, what is our go-to tool as computer scientists? A dynamic program. And this is something that has been proposed and talked about for the last 40 years. So suppose we have this operation, which is called a join operation, where we join these three tables, E, S, and T, employees, salaries, and taxes. We first look at the best way to access each single table. Then we look at the best way to access each pair of tables. Then we go to the triplet and so on. Now, as you can imagine, this whole graph of connections gets really, really big as the number of tables grows, because it kind of grows combinatorially with the number of tables that we have, right? So when we get in a new query, EST, and then say something that starts with use that relates to employees, I can't think of something on the fly, or ES, and gifts, we would like to be able to reuse some of that experience that we had solving this dynamic program for other planning instances. But today, most database systems start with a clean slate. It's because of this combinatorial explosion of problems, figuring out what to cache is really hard. So what does AI have to do with this problem? Rather than thinking about this as a discrete caching problem, let's cache all of our previous experience. Let's think about a database as a learning system. What can we learn from my past experience? I have a database query optimizer, and it has solved one instance of this planning problem. What can I learn about branches in this search that are likely good or likely bad in future planning instances? Treat this as a learning problem. So when we think about this dynamic program, associated with each one of these nodes is a cost, is some way of a database costing how expensive this operation is. We can really think of all of this as training data. What happens if we could build a model to represent what the impact of a particular decision is on the future outcome, the future cost? Essentially mapping the set of tables that we're joining together, or our particular decision, with its long-term cost, its cost to go. And this is exactly a statement of a form of machine learning, a form of reinforcement learning called Q-learning. We can turn this problem into a problem of estimation. In some sense, reduce the problem of planning into estimation. As we've heard today, a good way of doing this is neural networks. They're a great way of capturing highly nonlinear and highly complex functional relationships. And the idea is that once we get this model that represents the mapping between a particular decision and its long-term value, it's sort of seeing into the future. We can kind of greedily roll down this function to avoid having to build this big graph. We sort of can do this in linear time in the number of relations, assuming we have this model. Now, this model is going to be imperfect, but it turns out it might be imperfect, but it's actually very useful in prediction systems today. So we integrated this with this algorithm into PostgreSQL and Apache Spark. These are functioning data systems today. And we can improve planning times sometimes by multiple orders of magnitude while matching the execution times of their native planners. We actually do slightly better. Talk to me afterwards why that's true. It's an interesting story about priors and models. So what's really fascinating about this is a microcosm in data science, that we find this connection between this classical problem of join optimization and the deep Q-learning algorithm that Google has been using to play video games. Who would have thought that there's a connection between these two algorithms, right? This is really kind of interesting. But it really tells us what AI allows us to do. It allows us to rethink classical systems problems in a new lens. If we think about these as learning and adaptive systems, what opportunities do we have? And where I really, really want to go with this is query optimization is one problem that we've been solving for a long time. But what happens if we want to take those same principles to much more complex queries? Instead of talking about employee salaries and taxes, what happens if my query was over a database of videos? Find all cars that appear in both videos. Now, this pipeline doesn't just consist of joins and the selections and filtering and all of the classical things that we see in a database. It consists of these weird operators that can sometimes be learned, sometimes programmed. Sometimes machine learning is a moving target, so 2 new papers come out on arXiv, and there are a lot of new opportunities for using different models there. When can I replace this When can I replace an existing component with something that I found on the internet, right? So this is fundamentally a query optimization problem, right? It's like we have a query, we have a high-level specification of what we want to do. We want to find all cars that appear in both streams. Now we need to figure out the best way to solve it. What I want to be able to do is to have formal ways of approaching these kinds of search problems. And there are a lot of interesting questions here about precision, recall, latency, and memory usage in these kinds of systems, because the second that we start talking about learning, everything is inexact. We move out of the world of logical formalisms into the world of machine learning and imprecise and inherently uncertain computations. So we actually built a prototype system based on this idea, and we're slowly starting to move some of the ideas from query optimization in my past life into this new system that we're working on here at UChicago. And the moral of the story is, we've actually found that there's crazy headroom in this problem, right? Sometimes that if you choose the wrong choice of operators or the wrong ordering of operators or choose not to build indexes in the right places, you could be like 600 times slower. It isn't like 1 time or 1.5 times or 50% slower. It's 600 times, right? If you're not careful about where you're placing computation on devices, this can also be problematic. CPU versus GPU, in memory versus off disk. Now, interestingly enough, what's really new and what's really exciting to me is how these decisions actually correlate with accuracy. Because unlike the world of relational databases where accuracy is sort of guaranteed by virtue of the relational model, here accuracy changes. Two plans might have very different precision and recall characteristics, but might run faster. So it's an interesting multi-objective optimization problem. And that's really where I want to go with this. The idea is that if we could get really good query optimization, can this empower data scientists to approach their analysis problems from a higher level language than they would be used to, like take away some of those decisions? Thank you.
Questions for Sanjay? I should just leave this with you.
So I think you might be taking Dave's advice of being an optimist here, because one could look at that 600 times slower if you get it wrong and say, oh my goodness, if I get it wrong, I'm going to be 600 times slower. So I guess the question is, how do you put, how do you put guide rails on this thing?
I think there are a couple of really interesting research, like the space of machine learning for computer systems, I believe, is an extremely interesting research area, because the concerns in computer systems are safety. There are interesting concerns about latency too, right? Integrating our machine learning algorithm into the Postgres optimizer was really hard, because you know that overhead of calling a neural network is actually very significant in a highly optimized system, a system that people have been working on for 30 years. Milliseconds matter, right? But there are very few machine learning frameworks that execute at like sub-millisecond latency, right? So this is actually a really interesting problem that people often don't talk about. Safety is exactly the other one. A lot of our losses in Apache Spark, at least, the queries where we did badly were crazy predictions by the neural network. It did something that nobody would have ever thought it would do, just partially because it just got data in the wrong way, or the data looked at it funny. I don't really know. So I think the idea of safety is a big one, and I think that the second that we start putting machine learning, whether we're talking about networks or databases, we really have to start thinking about safety, and maybe part of it is falling back to program defaults. Maybe that's the simple solution here, that every time we deploy a learning algorithm, we have a rule-based system under the hood, and we fall back anytime a confidence estimate is low. But I think that this is sort of the frontier, and it's really asking hard questions in machine learning the second that we put these into critical systems that we trust. Cool. Yeah?
There are systems where errors are simply not tolerated. I mean, airline.
Yeah.
So do you see any potential of involving any AI in those systems?
I'm not going to comment on that. My focus is data analysis, so let's hope that we're not killing anyone with the plots that we're making in Tableau. But no, I think this is a really good question, right? I think it's like, when we start viewing machine learning as a tool in these systems, as a new tool for programming and a new tool for adaptivity, some of these gains are like incredible. I would not have guessed when we started this project we'd see a 200x improvement in the Spark query optimizer. So that's like, for user, that is real impact. We're actually in talks with Databricks about putting this in production soon, right? I mean, this is like a really big win for me. But there are these edge cases, right? It fails in ways that we traditionally don't see software fail, right? Because we're used to people sitting down, thinking hard about a program, thinking about all the inputs and outputs, and writing unit tests. It's much harder to do that, and maybe part of the thing is actually just coming up with a theory about software engineering around machine learning. I think maybe that's half the battle.
So, I'm sorry. There is one problem if things get slower. Another problem is if you get the wrong answer.
Yeah.
Is that a problem?
So in query this is an interesting question about problem selection. We chose query optimization because if you're wrong, you're slow. If you're wrong, you're not incorrect, right? And so one of the things that in both the Deep Lens project and the query optimization project that we did is we ensured that, well, by virtue of the relational database space, we have logical correctness. All the plans we search are exactly equivalent. And in the Deep Lens case, we have a type system that validates all of our inputs. So we make sure that nothing selected by any sort of automated algorithm will do something wrong. Now, it might be slow, but it won't be wrong. Now, I completely agree there's a really hard question of the second that we start having the algorithms do things that where correctness is not guaranteed by virtue, that'll be much, much harder. Awesome.
Hi, I'm Michael Maire. I recently joined as an assistant professor. I'm very grateful for the opportunity to talk here. My research is focused on computer vision and also associated deep learning techniques. So I'm going to give sort of high-level overview of a couple different projects that sort of represent major research objectives. So on the computer vision side, sort of a long-term goal has been to enable computer vision systems to understand scenes at a high level of detail. So this is sort of pulling out detailed localization and identity information of the objects in the scene. The computer vision research community over the past several years has been driven, to a large extent, main driver of progress has been curated data sets that have ground truth human provided labels. Particular note are ImageNet, which was a large scale data set of 1 million images, each of which was tagged with one of 1,000 category labels, and was sort of the driver for the deep neural network revolution in computer vision back in 2012. More recently has also been this COCO data set, which is the acronym expands to Common Objects in Context. And there, the labeling is more fine-grained in that there are sort of a set of 80 different object categories with multiple of these categories appearing in each image, and there's detailed localization and object boundary and outline information annotated. And then systems are trained sort of in a supervised end-to-end manner to try to recover this information from the images. So both of these sort of are operating in a closed world setting where we have a fixed vocabulary of objects that our system is trained to identify. At some point, though, we'd like to sort of bridge computer vision to the real world environments where we may not know ahead of time what objects are present and what types of entities we're going to encounter. So on the top here is a system from fairly recent work that is not trained to identify particular objects, but trained to recover grouping relationships. So the setup here in the diagram on the right is that there's this neural network module that predicts for 2 different locations in an image whether those locations belong to the same object, and then also if those locations don't belong to the same object, what the depth-wise discontinuity is. So is one region in front of or behind another region? So out of this neural network, it's trained to predict sort of these set of pairwise grouping relationships between locations sampled in the scene. And then from sort of the noisy output of these pairwise predictions, we have this embedding procedure, which you can think of as an optimization procedure that takes all of these noisy pairwise predictions and attempts to produce as output a globally coherent interpretation of the scene, which is what you see on the rightmost column here are our predictions in terms of a segmentation of the scene into objects, and the coloring, the red to blue color scale is predicted depth offsets, so relative depth. So we're interested in sort of coupling this more generic understanding of scenes with also our knowledge about known object categories in order to eventually start scaling computer vision to real world environments in which your system might want to extract and learn about and discover new objects in addition to the set of objects you already know. Coupled with sort of this effort to reduce the reliance on curated labeled data sets, we've been looking at methods for training neural networks that don't actually involve using any human annotation. So in the space of images, we can think about creating a proxy task for the network that involves splitting an image into an input and label pair automatically. So a couple candidate tasks are sort of recovering one portion of the image from another portion of the image. So we split our data into two different into two different pieces and try to recover the second piece from the first. And in this setting, for example, in painting here, it's a little different context than the in-painting type results Becca talked about earlier, because here we're viewing it as we sort of have an unlimited reserve of data, so internet images, unlimited number of examples, and what we're interested in as the output of this process is the neural network itself. So can we use sort of these proxy tasks as a way to train a neural network that has lots of useful representations about images, and then can we easily port that network to subsequent tasks that we're actually interested in with very sort of minimal additional training effort. One task that we found to be actually quite useful in terms of defining a proxy is colorization. So recovering a color image from a grayscale version of the same image. And this makes sense in the terms of training a network to recognize objects, because in order to coherently colorize a scene, it helps to actually understand what's in the scene, what objects are. So flamingos, pink is an appropriate color, but blue is not an appropriate color. The sky, blue is an appropriate color, and many other colors are not appropriate. So we have primed the network to sort of learn representations that are object-centric. We're also interested in the underlying details of the neural networks we use in these problems themselves. And in particular, goal here is to correlate sort of design details of neural network architecture with system-level capabilities. So what I'm showing on the top here is a standard convolutional neural network, which has sort of been the paradigm since going back several decades, in which CNNs sort of operate on a grid, tensor representation stored on a grid of fixed resolution. And then they have several sort of processing steps on this grid of fixed resolution that transforms one representation to the next. And then typically, if you're doing something like image classification, the resolution of these grids shrinks due to pooling and subsampling stages. On the bottom here is an extension of this type of architecture we proposed that is inherently multi-scale at each layer of the network. So we replace this operation across a single resolution grid with a operation across a multi-resolution pyramid. And in the first layer, multi-resolution pyramid, you can think of it in case of images as just corresponding to a multi-resolution image. But in every subsequent layer, what is actually stored at each of these resolution scales is going to be determined by the learned network parameters. And we have sort of this architectural widget here that actually implements sort of this multi-grid extension of convolution that transforms one multi-scale representation into another multi-scale representation. And the interesting thing to note here is just looking at the arrows in this widget, there is information flow both from coarse scale to fine scale and fine scale to coarse scale at every stage of the network. And if we do this and we sort of train and benchmark these networks on standard tasks like image classification, we significantly outperform the baseline CNN designs. We can get higher accuracy with fewer layers, or higher accuracy with fewer parameters or fewer floating point operations. And these are all operating on real images. We can also have sort of a qualitative advantage with these types of networks, is if we go back to just a very simple synthetic task here. One of the earliest tasks used CNNs were demonstrated on. A modification of that is this digit distortion task. So the task here is to take a deformed digit that appears somewhere in the input field of view and output a rectified canonical pose of that digit. So this is the target output. This is the output of a standard network architecture, right, trained on this task. Basically, it fails to learn the task, whereas the multi-grid network actually does learn to perform this task. And some investigation into the internals of what's going on in this network architecture is that the multi-grid network is able to exploit this scale space structure, this learned scale space representation structure, to coordinate an attentional strategy. So if you think about this signaling pathway up and down scales, it's sort of a shortcut for information to flow across the image grid. And that's what allows us to sort of achieve an attentional behavior with a very generic network design. So we're interested in other aspects of architecture as well in terms of enhancing capability as a whole. All right, thank you.
Questions for Michael?
So I'm just curious, you focus mostly on vision and images. Like, can this be generalized to other type of like measurement data, like networking measurement or IoT measurement? What kind of data structure they need to hold in order for this or your solution to apply to?
Right. So, yeah, I think about this in terms of. So really, the motivation for this, so background motivation for this comes thinking about multi-grid methods in numerical computation. And so I think that the fundamental property we're changing here is actually sort of, I think about it in terms of sort of information pathway length. So how long does it take in the network? Is there a short propagation pathway for one piece of the input to sort of another piece of the input? We think about it in terms of receptive fields of the network. And is cast in those terms, that sort of abstracts away a bit of the vision-specific nature of thinking about multi-resolution grids. So so I think there's potentially application to hopefully things like natural language processing or other areas that use neural networks but don't necessarily deal with images. And of course, multi-scale is very natural for images, but I think there's something else going on here in terms of the actual information propagation within the network itself.
For the multi-grid, are you doing this primarily to improve quality or to improve computation?
We went on both. So with fewer floating point operations, we get higher performance, and with fewer layers, we get higher performance. So that may be, partially a side effect of just multi-scale is the right thing to do for images. But if we go back to this chart, we're looking at there are some additional results in the paper. Here we're winning on performance for layers. We also have a comparison of a residual multi-grid network with a standard residual network where we cap number of parameters in the network, or we cap number of floating point operations, and we can get equivalent performance at fewer parameters and fewer floating point operations.
Okay, thank you. Can you get it on? Just so I can put it on top or close it as you want. All right, wonderful. So my name is Pedro. I'm going to be assistant professor here at the Computer Science Department of the U of Chicago starting next year. So very nice to see many of you who I've seen before in prior visits, and I'm really happy that that logo has changed from the last time I was here giving a talk. So I'm a researcher in the field of human-computer interaction, and in particular in my research, what I spend time thinking about is of this question, and asks the question of, what comes after the wearable devices. And let me just start by showing two systems that I built during my PhD. I'll separate the stuff that is old and the stuff that is new, but just to give you a sense of, I don't know the answer of what actually comes after the wearable devices, but I think some of these systems might influence the way we think of the future form factor, that is the size of computing devices. So this one is called Muscle Plotter, and I built this to try to extrapolate or envision a little bit what future computers could look like. So you won't see a computer, basically. So these are two car designers. They're doing what car designers do, which is to try to figure out which of these two drawings is most aerodynamic. Normally, you would stop here, go to a CAD program, and simulate the wind flow simulation, right? These fellows have this pen, which is a special pen, just in the sense that it's a digitizer. Everything you write, a computer in the back end is able to observe. And so they wrote Wind Tunnel 10, and a computer in the back end has simulated that sketch through a wind tunnel. And so now you're probably wondering, but well, how does the user know the output of the simulation? That's why we have simulators, because this stuff is not obvious. Well, the user does know. What's going on here is that there's these electrodes attached to the user's muscles, and you're guessing the rest. They're sending tiny electrical impulses to the user's muscles, and they're steering the muscles left and right. And so you kind of scan lines, and then you get the output of the simulation. What's weird about this is that, besides putting electrodes on people, what's weird about this is that the computer is a pen and paper, which is supernatural for car designers, right? So we're kind of putting the computer in a very different perspective. Let me show you another system of very different nature. So this is a virtual reality system in what you can also feel forces. This is very different from the virtual reality exists today in industry, in the sense that there's nothing to touch in virtual reality right now. So its potential and applications are extremely limited because, there's no physicality. It does not feel or resemble like the real world. So maybe there's no teaching and so forth that you can do in VR if you can't feel the forces of the objects you're holding in, etc. And this system, again, using the electrical muscle stimulation to move your own muscles, is able to represent forces. Here it's a wall, it could be other stuff. So going a little bit step backwards, my research objective is to really answer this question, how can interactive devices connect to users in more intimate and personal and direct manners? And turns out David Patterson actually gave an absolutely amazing introduction to the things, because I tend to start asking, how we got here to the mobile phone, and he essentially explained, well, we had mainframe computers when chips were really big, and the user and the device were not even sitting in the same room, right? How much time would you spend with the computer? Maybe 1 hour with a punch card. After that, we had the personal computer revolution. Personal as in it's yours. It sits at your desk. How much time do you spend on your computer? I don't know how long you work, but let's say 8 hours, right? And then at some point we got here, where the computer sits in your pocket. This is the one that should be called personal computer. That's really, really close. But you can start asking this question and questioning. You see the paradigm shifts. We go to wearable devices. Devices are in constant contact with your skin. They are able to take measures and understand also your physiology, for instance. And as these paradigm shifts occur, not just in the size of the hardware inside, but they influence the form factor on the outside. So they're relevant for me as a researcher in the human-computer interaction side. What gets really interesting is that the user is spending more and more time with the device. And so, you can ask my colleagues, at the human-computer interaction conferences, so what comes after this? And I can guarantee you, like 75% of them are going to say this: devices that are implanted. And for me, it's kind of surprising because I don't think this is actually the truth. So I think this is happening already to some extent, that people have cochlear implants and insulin pumps and pacemakers. I think the crux of the question is different. What is actually happening is that devices are not necessarily going to the body, but going to the interface, overlapping with parts of your body, to your sensors and actuators. I think that's more important than their location being inside of the body. And so I'll argue that actuators is interesting as well, because I'm doing the electrical muscle stimulation. But I think what's really, really, really important, you see in the talk and in my work, is that I'm kind of intentionally taking electronics out by reutilizing parts of the user's body, such as their muscles and etc. And that's why I call this devices that overlap with the body. In the example that you saw initially, you kind of now see the overlap in a different light, right? I'm overlapping with the user's muscles. So if I would ask you to draw like a hardware diagram of this system, it would be impossible for you, that's why it's called muscle plotter, to not put the user's muscles in that hardware diagram. Otherwise, the system has no output capability. The work that I did in my PhD was done together with Patrick Bowdish at EHPI, just graduated last Friday. And so, thank you. That's very kind of you. And there we were trying to answer the question, what happens if the new wearable devices would interact with the user's muscles? And so we're using this technique, which stems from medical rehabilitation. This was invented in the 60s, been used a lot until today for patients that have some motoric difficulties. And here we're essentially asking the question, okay, we know if we actuate with an electrical potential between two electrodes, we can move the human body, and so what sorts of things we can do. And you've seen one of them with this idea of giving physical forces in virtual reality. I don't have to show it again, but I think what's really interesting is that the alternative to this approach is essentially going back to the history of robotics and using really, really large exoskeleton devices. So this is essentially the same thing, right? Except it weighs 1 ton, it's bolted to the wall, another ton of batteries in the other room. So we're kind of just trying to juxtapose these two approaches and ask, in terms of an engineering question, you know, which one can we miniaturize quicker? And that one is, unfortunately, the exoskeleton subjected to laws of physics that say, you know, you can't really miniaturize a motor and then output the same force. And in other research side of it, we're also asking a little bit more conceptual question, which I really intend to continue here, which is what other channels can we use to communicate with computers? I'm communicating right now visually, most of you as well, sometimes auditorily when we talk to the computer, but what other things are in there? And so I've spent some time working on this idea that we would actually communicate to the computer using poses. And so what you see here is a work that I've done called pose input and output. And so I'm feeling the computer telling me what's going on with that variable rather than actually seeing that variable. So I can do this eyes free. And you could imagine this being, I don't know, Bitcoin prices or David's citations after the Turing Award going up massively, whatever that data represents. But you don't see it, you feel it, right? And so what's also really interesting here is that this is very different from the wearable devices that you might own or have experience in your life. This sits under your clothes, there's nothing to look at, and so forth. And it's input and output using the same language, the same vocabulary, and that is poses of the human body. I'll skip the boring stuff, how this is made. All right. What is interesting here, and this is already a little bit of what I want to achieve here at UChicago too, is, well, what if we apply this idea that the computer's talking to you, but not visually? It's not a YouTube video that you have to watch, but it's poses of your body. And let's apply that to a situation in your life where you have to do something physical. So there's a physical skill involved here. This is actually footage from a user study. And what we did here was to bring participants in and calibrate the muscle stimulation system, you know, the whole thing, and ask them to do a task that might seem trivial, which is to paint that drawing with a spray can.
Okay, that was cool. I totally would have got to shake it.
And so you start getting what's going on. People actually forget, when computer scientists forget to shake the spray can. And this system is in real time, not really teaching you, it's doing it for you. And by virtue of that, you start to understand. And so you can see that's sort of a simulated shake. All right. And so when you put these all together, the idea here is try to probe the future of wearable devices. So what's next? Interfaces for physical learning. trying to understand if this is indeed one thing that is better than watching YouTube videos for acquiring a new skill. Perhaps it is. And for that to be answered, there's a couple of more complicated questions. One of the things that you need to understand is when that device is doing something to you, do you feel like it's you doing it, or you feel like an external force? And so this is what I'm answering with Jakob, Carl, and Felix. We're trying an experiment where we're actually putting people inside an fMRI brain scanner so we can kind of understand what they're thinking about, what part of agency is thinking about. And we're trying to ask them to do a very simple task, which is to tap to a beat, but sometimes we'll do it for them, and we're kind of trying to understand that. Same here, but with another technique. This is together with Klaus. We're using BCI, so kind of electroencephalography, to understand at the scalp level what can we measure of your agency doing certain tasks. All right, this obviously has implications too. That's why we were laughing at the beginning, right? And so to tease a little bit on that note, I've done an art piece that was shown at Ars Electronica that tries to reverse this idea. Okay, well, if machines indeed control you, then you're losing agency. And so this opened up a question for 200,000 visitors to actually start to ask it and deeper think of it. So this is a machine that actually traps people inside. And so the question that we're really going to focus on for the next years is what comes after wearable devices. And that's going to happen downstairs, thanks to this new building, beautiful Crowd building. And you can also come see some exhibition of weird microcontrollers that we have there. But also would invite you after this and after the celebrations, if you want to come downstairs, talk to my collaborator, Jun Nishida, who's visiting us today. He's from Tsukuba University. He might or not come here. That would be really nice. And Jazz Brooks, my PhD student here at UChicago, who's also working on this. And that's it. Thank you.
Questions for Pedro here. So, do you see the potential for sort of corrective action, like for people who have diseases like Parkinson's, for example? You can use a feedback and muscle stimulation to correct sort of involuntary body movement and things like that?
Yeah, you should actually check out Jun's work. He has done some work on that. I have looked into that for a little bit in 2016, and because Rob said that the talks are being recorded, I can't say a lot of it yet. But let me tell you offline that it kind of works to some extent to help regain or to easen up the tremors. But there's more complicated things. So yeah, there's some small possibility that it's impactful in that space. Very good, very, very good question. There's a question here too. I'm curious about that.
Hi, so I really like your project. So like my question is like, is it possible if we can like use your muscle simulation to implement the motion capture?
To say again?
Is it possible to implement like motion capture?
Oh yes. Again, you should talk to Jun Nishida. So yes. So in that project where I was moving my hand up and down, I was able to also do the opposite of muscle stimulation, right? So in muscle stimulation, you're putting electricity in those two electrodes that causes involuntary contraction. It is possible, because your neurons are small electrical machines, to do the opposite. You measure, like a multimeter, you measure those, the voltage on those electrodes, and you find out the voluntary contraction. Now, that does not give you absolute position, because as you know, it is possible to move your muscles, called isometric contraction. I'm tensing this one and this one, without moving that part. So it's kind of a relative type of motion capture that you would be able to get as a result. So it doesn't kill the Hollywood industry yet. They would be interested in that.
Yeah, one last question.
Would the drawing thing help you play piano?
Yeah. So I can tell you you're very creative. The only reason why I didn't show piano is because I can't do it. So there's some limitations in how much you can actuate individual fingers, and that's because the muscles are layered and it's really hard to access individual layers. But one of the things we're probably going to work on is rather than having these electrodes placed by an expert, having a grid with many, many electrodes, allowing us to maybe not to piano that quickly, but to simpler tasks like juggling a ball or something. And so bear with us. In a few years, maybe we can help you.
So then,
thank you, Pedro.
Yeah.
Great. All right. Thank you. So the amazing thing is all those people you heard from weren't at the University of Chicago prior to July 1 this year. So, and some of them still aren't here. So lots of things going on, lots of changes. So with that, I'd like to thank all the speakers and invite you, everybody, to the reception, which is starting now in the back. Thanks.